I was initially planning to be at Hils for 2 months. That did not happen. I did not succeed in going there, but so I will give a talk from here. Before I start, let me do some publicity very briefly. So there is a new journal on model theory. It's just out for 2 weeks, and you are very welcome to submit to this journal. It's by MSP, and I won't let the slide on for longer. So remember, a new venue for our work. Okay, so now let me do this so that we get the right camera. I hope you can see it. Else, please protest. I should hear when there is something to say. Okay, so this talk, first of all, this talk is joined with Pablo Cupides from Düsseldorf and Vincent Ye from Paris. It is about spaces of definable types and beautiful pairs in unstable theories. So I'll start with the motivation. In the second part, we will see the general context for beautiful pairs. And in the third part, I will give applications to the model theory of valued fields. So what is the motivation? Let T be a complete theory. Say L theory. U a monster model. I will use this notation all over the talk. Recall that a global type, so a type over U, is definable if for every L formula, say this is a type in X, say, for every L formula phi of x, y, there is a uniform decision of what instances of phi are in the type. A formula which may have parameters, L of U formula, which is usually called dp phi of y, such that for all c from U to the length of y, we have the instance corresponding to c, so phi of xc is in the type P if and only if U says dp phi of c. In this sense, it is definable to decide which instance of phi is in the type. Now, we say that T has uniform definability. Uniform definability of types. If over all definable types P, there is the defining formulas dp phi can be chosen within a single family. So if for any phi of xy, there is an L formula psi. Let me indicate psi phi. So just psi, which has in y z, such that any phi definition of any definable type may be chosen as an instance, so as psi phi of y and some parameter d, for some d. So we all know in the stable theory, all types are definable, and even so uniformly, for example. Okay, now if T has uniform definability of types, we can go a level up to the meta level, and we can treat spaces of definable types as pro-definable sets. So let me make this precise. If T has uniform definability of types, choosing some C if as above, for any definable set X, maybe with parameters, the set S X def of U, these are the definable types, global types, concentrating on X. So this is the set of P in S of U definable, P concentrating on X. So containing the formula X is in X, is naturally pro-definable. Is naturally a pro-definable set. So this is very useful. Namely, it can be itself considered as an object of model theory. So how does this go? Via the map, okay, I send a definable type P living on X to the sequence of the codes of the defining formula. So dp phi, phi, and L formula. So this is a infinite tuple. So with the corner, I indicate that I take the canonical parameter. So this is a tuple in UEQ. Okay. Now, why is this more precisely?
We don't see the bottom.
Yeah. Yeah, you cannot see the, okay. Now, can you see it?
Nope.
I see. Yeah, I cannot write, okay, at some point it will disappear because I cannot. Okay, now, more precisely.
Why don't you put it all the way up? And then
I will put it all the way up, but I will quickly run out of, okay. More precisely, it is a pro-definable subset of the product given by all the sorts, given by canonical parameters of instances of C phi. So a pro-definable subset of the product, let me call these sets Q C phi, where phi runs over the L formulas, where Q C phi is just equal to the set of canonical parameters of instances of C phi. So any such set is a subset of UEQ, definable subset of UEQ. Okay, and this Sx def of U in a canonical manner gets a pro-definable subset there. Okay, now I have to move up. Sorry for this, so it will disappear here. So why do we care? Well, there is the work most of you are familiar by Ruszowski-Leuzer on the, well, they gave a model theoretic approach to non-Archimedean geometry, basically mimicking a Berkovich identification of a variety defined over a valued field with a space of definable types. So what is this precisely? So think that we are now in ACVF, so the theory of algebraically closed valued fields, non-trivially valued fields. For X definable, let X hat of U be the set of definable types living on X such that P is stably dominated. This means the stable part of HCVF is given basically by the residue field, and this means that you have a good control of these, a complete control of these types generically by a map to the generalized residue field, let's say. But they show that this set X hat is actually strict pro-definable, which is much better from a point of view of model theory, because more compactness can be used. What does this mean? Which means if you have a pro-definable set, you can always project down to the coordinates. Yeah, for example, here in this product, I realized as x def of u as a sub, the pro-definable subset of this product, and we may ask, if I project to the coordinates, do I get a definable set or do I just get a type definable set? It's always type definable, but when it is definable, which means that I will explain now, strict pro-definable means it is pro-definable. So a pro object in the category of definable set, and the projections onto all the q, did I call them? Cube psi phi, so on the coordinates are definable. Yeah, they are always, let me say, they are always type definable for a pro-definable set, but here we want more, always type definable, but here we want actually definable. So this is a crucial ingredient in the work of Hrushkovsky-Leuzer. Yeah, and so just remark X hat, so for V variety, then V hat is a model theoretic analog of the Berkovich analytification N.
Martin, there's a question in the chat. Are the projections definable or the image of the projections definable?
The image. But wait, I mean here with projections, the image of the projections. Okay, the images of the, so yeah. So you project onto the coordinate, and what you get in the coordinate is always type definable. That is completely easy to see. That follows from the mere definition of pro-definability, but you want them to be definable. What does it mean? You want to be able to say definably whether an instance of the formula is the phi definition of, in this case, a stably dominated type. And in general, it will be, it is the phi definition of a global definable type. Next, yeah? So the image of the projection. Thanks, Dave. Okay, so now I come to the motivation of this. I will not talk about, this is a long story. Most of you know this story. Let's just let it stand as it is. So this is an important object. And I want to come to the motivation of my talk. So Pablo and Vince, they showed that ACVF has uniform definability of types. In Hrushkovsky-Leuzer's work, you only needed that for the stably dominated types, where it is stably dominated is the same thing as, maybe I should say this, stably dominated is the same thing as generically stable. Generically stable, which is the same thing as orthogonal to gamma. So this is an important equivalence in ACVF. And so uniform definability of types for stably dominated types follows by the fact that in every NIP theory, the generically stable types are uniformly definable, which comes from the majority rule. But in ACVF, this is something, this is for all definable types, they showed this. Okay, good. First thing. And they introduced a model theoretic analog of the Huber analytification. So let's give it X tilde. Yes?
Martin, another question from the chat is, what does UDT mean when not all the types are definable?
It means that all definable types have, there is a unique, for all definable types, for any formula phi, there is one formula which gives you all phi definitions. That's what it means. Not all types are definable, but whenever, okay, there is, for every formula phi, there is a formula psi such that all definable types have a phi definition coming from that family. Okay?
Thank you.
So that's it.
Martin, can you hear me? Can you hear me, Martin?
Yes.
You hear me? Yeah. So does this also work locally? Just suppose you have definability of the phi type.
That I'm not sure. I don't want to. I'm not sure. I thought about it when. I'm not sure. I don't want to. I'll think about it. I'm not sure. At least the technique, because we are reproving it here, but I'm not sure actually. We are reproving it here for complete, for like globally definable types. Yeah. Okay. So I will come back at the end to what you are asking. So they are introducing a slight variant of the Rogowski-Lazare space. Take now the definable types, say on X, which are orthogonal, or which are bounded. P is bounded. And where bounded means, i.e., bounded is equivalent to orthogonal to the type at plus infinity. So whenever you take a rational function and take its value, you must be bounded. So you cannot go to plus or minus infinity. Okay? So this is a model theoretic analog. You can look at it of the Huber analytification. But here's the question which motivated our work. The question is S def x of u or x tilde of u strict pro-definable. So I should say that Pablo and Vince showed that both are pro-definable. So the point is, are they strict pro-definable? Okay. So I will answer this question, or we answer this question by going to some more general property, which involves beautiful pairs, and by establishing an X-Cauchy-Yershov theorem for this. And then both questions will become very easy because we only have to check them for divisible ordered abelian groups and for algebraically closed fields, so for the value group and residue field. Are there questions so far? Yeah, so both will have a positive answer, but coming from a more general principle, which allows us to reduce such questions to residue field and value group completely in the X-Cauchy-Yershov philosophy. Okay. So let me come to the second part of the talk. So beautiful pairs in an arbitrary theory. I should say that this has nothing to do, or is rather orthogonal to the generalization of a belle pair of Poisson to the simple unstable context. It is on the definable side of things and not on the non-forking side. Okay. So for this, let's assume T complete with QE, so quantified elimination, and uniform definability of types in the sense I explained before. Choose uniform defining scheme as before. So this is all done. Now let's go to the main, well, the main object of the talk. So definition, a parallel structure. A parallel structure is a structure.
Is that a parallel, P-A-R?
Parallel, like pair, but you take away the, yes, like pair, parallel. A, like it has, so part is on the predicate and part is the set itself, where A is a definably closed subset of the monster in the reals. So U is still a monster of T, and P of A is an elementary substructure of UEQ. So in P, we also add imaginaries in the predicate, such that the type of the L type of A over P of A is definable. So this is now a type over model, so there is no question of stationarity. Okay, we work in the language which I call LBP. You can choose if you think of Bruno Poisat or beautiful pairs. So LBP is given by, well, you have the language of pairs, and you add function symbols for the defining scheme. So F phi, where phi is an L formula, such that F phi of a tuple A is equal to the code of the type. So where P is the L type of the tuple A bar over the P of A. So you send the tuple from A to its canonical base, say, yeah, for all. Okay, good. That is a parallel structure. Now CDEF is the class of parallel structures. With embeddings, so note, if you have A embedded in B, then by our definition of F phi, we get that the L type of A over P of B is just the canonical extension of the L type of A over P of A to P of B. So this is just built in the formalism because we named the canonical parameters. So we need a little bit more. We don't want to always talk about all definable types. So we say that C in CDEF is a natural subclass if closed under isomorphism contains MEQ for all elementary substructures of U. So it contains somehow the trivial pairs where you don't have points which are not in the predicate. Closed under base change. Base change just means that you increase the predicate. There is a canonical way of adding because you have the defining scheme, so you can just add elements. I mean, it can make the ground model P larger, and you have a base change. And finally, and such that A P of A is in the class if and only if A0 P of A is in C for all A0 finitely generated over a P of A.
Martin, there's a question from
Yes.
Derek. Do we need to know what A is in order to specify the language?
Sorry?
We need to know what A is in order to specify the language.
You need to know what A is in order to specify the language. No, we don't need to know what A is.
Well, you said we work in the language LBP given by
Yes.
the language
So
P union the set of these functions.
We have P, so a predicate, and on the predicate, actually, we add all sorts from TQ.
Yes.
Just because we want to add these functions. So we want to add function symbols, F phi, such that they are interpreted in this way. Whenever you have a tuple A bar from A, okay, I should add it for all A in A. Whenever, so a parallel structure is so the type of A over P of A is definable, but I add the canonical parameters with a function to it.
Right. Okay. You're adding the function symbols, and then afterwards you're
symbol,
telling me how those are interpreted.
I force that if I have an embedding, I force that the embedding is nice.
By the way, it's not true, is it, that PA is contained in AQ? It's not true, is it, that PA?
No, it's not. Well, it is true because P of A is a mod. Okay, yes. So that I should add it. You can add it. Assume you can add it. P of A is in AEQ. Yes, you can add it. So the real part of P of A will be a subset of A because it doesn't matter. You can always add it. Okay. So you may assume it. Good. Example. In ACVF, the bounded parallel structures form a natural class. Or the stably dominated parallel structures form a natural class also. Okay, good. Now, what is a beautiful pair? So, P of M is, okay, let's take an element of C. So assume that we have a natural class, is a C beautiful pair. C beautiful pair, I abbreviate it with BP, a C beautiful pair, if it is L plus rich for the class C, which means that i.e. for any A in B, this is an element of C, B not to, so B of cardinality at most L, in M, I can extend the embedding to an embedding from B to M. So just in the usual amalgamation sense, it's a rich structure in the class. Okay.
So, Martin, what is bounded parallel structure in the ACVF?
So I defined it.
What did you define?
I defined in ACVF a bounded definable type is one which is orthogonal to the type at infinity. So equivalently, if you realize it, the old value group will be cofinal in the new one. Okay?
Okay, just a realization of this type.
So this is in ACVF. Yeah. Bounded just means that you are orthogonal to the type at infinity in gamma, or equivalently, if you realize the type, the old value group is cofinal in the new one with the realization. Okay.
By the way, Martin, could you briefly in one sentence remind us what is a beautiful pair of stable?
Yes, I can remind you. I will say it loud, but not writing. So a beautiful pair, a belle pair of Poisson is the predicate is saturated, say enough saturated, and the full structure realizes every type over the predicate together with finitely many parameters. But you can also take cardinality of L many parameters. I will make a, so this is of course, yes, Anand?
In the original language.
Yes. So I mean, Poisson did not add these functions, but okay. Of course, this is building on work of Poisson. The definition: assume. Now let me first give some. Sorry. Let me first give a couple of. Sorry. First a couple of facts. So facts. facts. 1. C beautiful pairs exist if and only if C has the amalgamation property. This is by standard amalgamation techniques. Moreover, if C has AP, all elements of C embed into a beautiful pair. Okay, good. First thing. Second thing, so this is general, I would say general nonsense. Assume now beautiful pairs exist, so equivalently the class has the amalgamation property. Second, any two beautiful pairs are actually L infinity equivalent, in particular elementary equivalent. Set TBP of C, the common theory. And I will write, I don't write it on the board, I will write TBP if the underlying class is the class of all definable types, theory of beautiful pairs in the absolute. Okay, 3. Beautiful pairs, C beautiful pairs are elementary pairs of models of T if and only if C has the following extension property, which man might also call Tarski-Ward property, which says that if A, P of A is in C and Phi of X a consistent L of A formula, there is an extension B, P of B, containing A, P of A, such that phi of B is non-empty. So you may solve. And if you have this property, then beautiful pairs are elementary pairs. But there are examples where you don't have this property. Okay. Now let me give an important definition. So assume the class has the amalgamation property, so beautiful pairs exist. We say this theory of beautiful pairs has beauty transfer. If there is a L plus saturated C beautiful pairs, equivalently all C beautiful pairs are L plus saturated. Okay.
Martin, the question is A necessarily a model?
No, A is not necessarily a model. A is a definably closed, in the sense of L, subset of the monster. Yeah? Okay. Proposition. Assume TBP of C exists and has beauty transfer. So in the good situation, it may coexist that you are beautiful and saturated. Then TBP of C has QE. Secondly, P is purely stably embedded. So no new induced structure. And thirdly, this is why we do this, for every X definable, L definable, as X def of U is strict pro-definable.
What is purely stably embedded supposed to be?
It means it's stably embedded and the induced structure is just coming from LEQ. So proof of 3. Yeah, what you do is X of M, if M is a beautiful pair, EBP of C. I should not say this. So the definable types, sorry, C definable type, okay. These are the types, if you restrict to C, I'm sorry. So this includes the situation where C can be arbitrary. So those definable types giving rise to parallel structures in C. So this should be C. Okay, take a model, then X of M goes surjectively onto Sx C of P of M. A goes to F phi of A, phi L formula. And if you compose with the coordinate projection, you get a definable map. So that's why the image is definable, which shows the result. So you have strict co-definability. Now I come to Anand's remark. So the stable case, Poisson, if T is stable, then CDEF has always the amalgamation property and the extension property. So beautiful pairs are always elementary pairs. And TBP, so of the whole class, has beauty transfer by Poisson if and only if T is NFCP. If and only if Sx def of U is strict pro for every X. So this is in the stable case, this is equivalent. So beauty transfer of beautiful pairs is equivalent to the question I'm interested in having a positive answer, namely the spaces of definable types are strict pro-definable. So this is by work of Poisson, and we are generalizing his work to the unstable setting. Okay, so let me just give a couple of further examples. Unstable examples. DOAC. So here, by Marcus Steinhorn, in any O-minimal theory, in any T-O-minimal, if you have an elementary pair, then type of n over m is definable if and only if type of singleton A over m is definable for all A in n. Okay, so being a stable embedded pair, being a definable pair is first order. Let
Martin?
TS, yeah.
Sorry, there are two questions from the chat. One is,
Yes.
does the QE you're talking about here coincide with DeLong's quantifier elimination?
Yes, it does. In the particular situation where you have ACF, her language is very specific to algebraically closed fields. Exactly, yes.
And the second was just as if you could repeat the definition of a beautiful pair.
Beautiful pair is a rich element of the class, so you can solve amalgamation problems. You have something embedded. If it's not too large, say cardinality at most L, you can embed it over what is already in it. So you have a rich element of the class. Very standard thing. So let TSE be the theory of stably embedded pairs, elementary pairs of models of T, then DOAC SE has 4 completions, namely set E0. There is an X such that X is bigger than 0, and for all Y, if P of Y and Y bigger than 0, then X is smaller than Y. So you have a realization of 0 plus, and E infinity, same thing. There is an X. X is for all Y. P of Y implies Y less than X. So there is a type at infinity. Then has 4 completions. The completions are given by yes or no for E0, yes or no for E infinity, and you can combine both. So either realize nothing, then you just have a trivial pair, or only at 0 plus, this is the bounded case, or both, this is the complete case, and all are theories of beautiful pairs for appropriate classes, appropriate natural classes with beauty transfer. So everything is nice. So since I'm running out of time, I want to give the application. I only have 5 minutes left. Let me just say in the air 2 further examples. One is Pressburg arithmetic. The theory of beautiful pairs is just a theory of proper end extensions, and it has beauty transfer. Another example, for an arbitrary or minimal theory, Anand has described a theory which he called T star, and we can show that T star, it's not clear that it's consistent. If it's consistent, it's complete, it depends. For example, if you have a model living on the reals, then it is consistent. And we show that it coincides with the theory of beautiful pairs, and it has beauty transfer. And so Anand's theory T star, for those who know, is consistent if and only if the class of the pair structures have the amalgamation property. That is a cute corollary of what we are doing, I think. Okay, but let's come to the third part, which I will leave brief because I only have 5 minutes left. So the point is, in Henselian valued fields, the equicharacteristic 0, or in algebraically closed valued fields, the question whether or not beautiful pairs exist and whether or not you have beauty transfer obeys an X-Coach and Ershoff principle. So application to valued fields. But let me just formulate it for ACVF. KV is a valued field. Let me take it ACVF. Yeah? I restrict myself. Okay, so Cubides-Delon. Showed that if you have K in U, so a model of ACVF, and K in L in U, a subfield, then type of L over K is definable if and only if 3 things happen. First of all, it's true for the residue field as pure fields. Secondly, gamma L over gamma K, the value group, is definable, type of, okay? And thirdly, L over K is a separated extension in the sense of Bauer. Namely, every finite dimensional K subvector space of L has a valuation basis. Good. With this characterization, we can show our main result. Do I have 2 more minutes to state it? Dave?
Yes. Yes.
Good, thanks. Sorry for this. Okay. So, so just for ACVF, everything I'm saying now is true for Henselian equicharacteristic 0, and I will somehow give you the absolute case, and the relative case is similar, and the way we prove it is really X-Cochin-Yershov-wise. So we do it, the proof is the same for Henselian. So you can combine, as you wish, the natural class on the residue field and on the value group, and you get a natural class in the valued field, and axiomatization is the easiest possible. So theorem. Okay. Let C res be a natural class in T res, which is now just ACF. Okay. In general, it can be in a Henselian setting, it can be something else. C val, a natural class in T val, which is here just Stoic, but it could be more general, a theory of the value group, having amalgamation and extension property, assume the beautiful pairs in these two settings have beauty transfer, so everything is nice. Beauty transfer. And then the same holds for the class I can cook up. Let C be the class induced. Let C in CDEF, in ACVF, be the class induced by these two, C res and C val. This works in general in the Henselian setting. Then TBP of C exists and has beauty transfer and is axiomatized by so L over K is a separated elementary pair. Group pair, oops, is a model of
Bert?
TBP, yes, of C-val. I'm done. Yes. Yes, Dave?
Sorry. Nothing.
So this is the theorem. As a corollary, we get a positive answer to the motivation questions because we saw that for C-val, the bounded types in DOAC, which are very easy to handle, we get, and for C-res, just the theory of beautiful pairs, so proper algebraically closed pairs of algebraically closed fields, we get a nice theory, and we get strict definability. Similarly, if we take the full class in the residue field and the full class in the value group, then we get all definable types, and so we get strict definability also for the space of all definable types in ACVF. And similar results hold in the Henselian setting because it's a relative statement. Okay, thank you for your attention.
Thank you, Martin.